All right, talk is solving engineering problems using theology. You might say, how on earth did you come up with this subject? I'll give you the answer, and that is that Luke said, why don't you do a talk? I said, what do you want me to do it on? And he's like, whatever you want. And that's always a bad idea to say to me. You know, my wife actually, you know, she knows not to let me wear whatever I want out of the house, because that's a bad idea. Likewise is letting me talk about whatever I want. That's also a bad idea. So you wind up with topics like solving engineering problems using theology. So, anyways, I start up with a quote from one of our lead developers. Theology and science are like peanut butter and chocolate. Life is basically a giant Reese's cup. So anyway, I just had to throw that in there because I posted to Slack what I was talking about and made that quote. So I was like, perfect. We'll do that. So a quick note about me, kind of, this is why I thought of something like this, is that my actual training is as a theologian. I graduated from Phillips Theological Seminary with a master's in theology, but I'm a practicing software developer. So I also do independent homeschool education, and I'm an all-around wannabe writer. So hit lots of different topics on programming and other things. So the most of this is actually going to come out of these last two, which are conferences that we did on integrating various disciplines. So, theology. A lot of people have a very narrow view of theology, but I have a much more expansive view of theology, and that is, theology is not just about God, it's about the things that kind of come after that as well. So, what's the nature of the universe? What's the nature of humans? What's the nature of the mind? Pretty much all the things that are general, your whole holistic view of the world is encapsulated in the term theology. What's the purpose of life? What's the nature of beauty? What's the nature of sin? What's the nature of morality? These are all theological questions, and that they're even theological questions if you answer them from a non-theistic standpoint, right? Because atheism is a theology. There's multiple atheistic theologies. It's not about whether or not you believe in a specific way. It's about whether or not you answer questions such as these. So, so then the question is, can theology be useful? Because a lot of people think of theology and they think of people sitting around thinking or reading and coming up with self-congratulatory answers that don't really impact anybody at all. Okay, but that's kind of where it's gone in the modern era. But actually, historically, it's actually been quite useful in underpinning a lot of the things that we take for granted today. Our system of government is actually based on the founders' view of sin. So their theology of sin influenced the way that they set up the government. Because that's why we have three branches of government, because their view of sin is that you can't entrust everything to any one party, that since no one can be trusted, we're going to have multiple parties and set themselves against each other. So anyway, so all these things actually wind up being theologically based, even if we don't use those terms, and sometimes even if we're not consciously thinking about it. A lot of the things that we do come out of the theology of previous eras that we just kind of hung on to. We don't even know where they come from. We just kind of ride the wave. We kind of assume that that's the way it always is, but it's really not. It actually came from specific theological thoughts. So the special focus today is theological anthropology, which is the theological status of humans. In most theological views, humans are both material and spiritual. And in this case, it means that no material-only system can substitute for a human. Now, if this is true, then that also means there's a difference in the abilities of humans, which are material and spiritual, and computers, which are material only. And like anything else in life, if there's a difference, engineers can exploit that difference for various purposes. So, my primary goal is to just get people to think about these ideas more deeply. Think about where these different ideas about humanity intersect with our ideas about programming and software development, and then encourage people to use theological thinking in productive ways. We're going to start out with the history of computers, okay? Because most people don't realize that computers were not invented primarily to solve a technological problem. They were used to solve technological problems, but they were not invented for that purpose. They're actually invented to solve a philosophical and theological problem. There's a question is, are there transcendent properties of the world? And so the idea that are there things which transcend scientific explanation, okay? And so David Hilbert represents the materialist camp, and he developed what he called the formalist school. His idea was that that once you have the base set of core truths, that you can mechanically derive every other truth from them. Okay, you can do mechanical deduction from first principles to any given truth. Okay, and this created what's called the decision problem, and it's questioned whether a procedure could be developed that, given a logical statement, you could determine the validity of that statement by simple mechanical deduction from first principles. Okay, so if materialism is true, at least in the Hilbert conception of it, then that means that we can deduce all true knowledge from foundational principles. The other side of it says that there are true principles that actually transcend this ability to mechanically perceive them. So in 1931, Gödel proved that any system that's at least as complex as arithmetic, there are statements about it which are both true and unprovable within the system. Okay? Now his proof was very arcane, so people kind of ignored it for the most part because it dealt with prime numbers and factoring and using numbers to represent symbols and was very difficult to work with. So Turing developed his formalization of what it meant for a procedure to be mechanical or automated, and that was the Turing machine. And so by inventing the Turing machine, he defined what it meant for a process to be automated. Okay? And his whole purpose of this is to solve the decision problem, to answer whether or not Hilbert's goal of finding out if we can deduce the logical validity of statements from a fixed set of axioms was possible. And in this first paper, the first paper that introduces computer science, we find out that no, Hilbert was wrong. There are true systems which are unprovable within the system. Both Turing and Gödel showed that there were truths that could not be known mechanically, but they both believed that intuitional knowledge was available and non-mechanical that allowed you to access at least some subset of these truths that you could not arrive at mechanically. Turing's next big paper is Systems of Logic Based on Ordinals, and it explores modes of logic that are explicitly beyond what's possible with Turing machines. Okay, and he called those oracle machines. Okay, and so his idea behind this is that although there's not an exact equivalence, that an oracle is essentially an intuition machine, something that is capable of, that is explicitly non-computational, but is capable of generating intuitions. Now, Turing actually changed his view after World War II, and he thought that the mind could be automated, although he never was real clear on how that might work. When asked about the relationship of intuition and mechanization, he was very unclear in his answers. But Gödel continued in his anti-mechanistic stance. Okay, and so the rest of this talk will mostly be from Gödel's perspective. And so modern computers were actually originally invented to solve a philosophical and theological problem. I think that's interesting in and of itself. That here you have this philosophical problem, and the tools that we develop to solve the philosophical problem actually wind up transforming the whole world. And it's because they thought deeply about the question is, can you have a automated mechanical procedure to do X? Okay, and so in order to answer that, you have to come up with what does it mean to have an automated mechanical procedure to do X. And so then they invented what it meant to have an automated mechanical procedure, and then that went on to change the world. And once that happened, though, the theological questions got kind of shoved to the back burner, and people kind of forgot about it. One person who didn't forget is Gregory Chaitin, and anyone who ever, if you YouTube, you should look up Gregory Chaitin. His videos are phenomenal. So Turing's new conviction that minds and machines were equivalent actually became the default presumption of future scientists. So future data scientists kind of assumed that minds and machines were basically equivalent. And so the research program of strong AI is the continuation of Turing's thought on mind and machines. And if you don't know the difference between strong and weak AI, strong AI says that there's nothing fundamentally different about the human mind and computer. It's just a matter of more computation until we get to the right space. Weak AI basically says that we can program computers to emulate all sorts of things, but there is a fundamental divide between what computers can do and what humans can do. This question has been largely left alone for almost 100 years, probably about 50 years. But it's the 21st century, and it's time to rethink some of these things. So the problem that Alan Turing came up with that showed that the decision problem didn't work is what's known as the halting problem. Okay? And the halting problem says that if you have a computer, there is no computer program that you could write that could take any other computer program, any arbitrary computer program, and figure out if that program will ever stop. Okay, so if it will ever complete, right? So we can't have automated infinite loop detection. So I have a more formal statement of some of these things in a paper of mine called Using Turing Oracles in Cognitive Models of Problem Solving. So the other thing, so this is a ultimate kind of a hard stop limit for what computers can do. In practice, it's actually much shorter than that, but that's kind of the... Now there's a question of whether or not humans can do this as well. Obviously, we can't do it instantaneously. We can't do it perfectly. Whether or not that, again, I explored that further in my paper. So there's not enough time to get into all of that. The same problems identified in the 1960s for strong AI still exist today. The very same ones. Some of them are the frame problem, that is determining which features are important. I forgot all the names of them, but anyway, they identified a set of problems around language and around data in the 1960s, and we actually still have the very same problems today. These are things that computers essentially can't solve, but that humans solve very readily. Thus, new directions in engineering are focused on not solving strong AI, but instead offloading problems that require non-mechanical beings to solve to the non-mechanical beings. Okay, so Peter Thiel, he's one of the co-founders of PayPal. He wrote a great book called 0 to 1, and I recommend anyone read it because it's fantastic. And so what he said, said computers are far more different from people than any two people are different from each other. So in 2012, one of Google's supercomputers made headlines when, after scanning 10 million thumbnails of YouTube videos, it learned to identify a cat with 75% accuracy. That seems impressive until you remember that an average 4-year-old can do it flawlessly. When a cheap laptop beats the smartest mathematicians at some tasks, but even a supercomputer with 16,000 CPUs can't beat a child at others, you can tell that humans and computers are not just more or less powerful than each other, they are categorically different. Okay, and so the engineering problem will be in figuring out kind of where this divide is and exploiting it to the greatest gain. So the field of human computation arises out of the failure of strong AI, and human computation offloads certain tasks to humans that computers can't handle. Some of the people in human computation actually think that computers could do them in principle, but it's just not practical to build those things. But I would argue that expanding and reflecting on a theory of human spirituality will help us to know more definitively which tasks require human input. So where are the lines? And so I don't claim to know exactly what the lines are, but these seem to be kind of where they line up. Humans appear to be uniquely good at creativity. That involves thinking outside of constraints and finding new system axioms. And that finding new axioms is the thing that where Gödel said that being able to find things that are true but unprovable. Those things are new system axioms that aren't determined from the other ones. Oh, I forget the name of the paper. There's a great paper that's on that. So determining what's important and what's not important. Gestalt reasoning, that's kind of a restatement of the frame problem, identifying identifying what's important, identifying the generalizing at the proper resolution, and then parameterizing. Parameterizing is very interesting because a lot of research today shows that, so for example, in medical diagnosis, computers are better at diagnosing problems than humans are, except for one thing. Coming up with the diagnostic criteria, humans are better at. Okay, so humans are much better than computers at identifying the parameters of the problem, but computers are much better than humans at both weighing the parameters and applying the parameters. So it's very interesting. This is there's a book called How to Measure Anything. The guy goes through different statistical models and how you can take things that you never thought you could measure before and make measurements. And this is one of the things that he pointed out from that has been found over and over, that humans are capable of creating parameters very, very well. Computers are very bad at it. So computers are uniquely good at applying rules, processing large amounts of data, analytical reasoning, and optimizing the usage of parameters. And so I think there's a good synergistic flow between humans and computers that produces, this is kind of what has produced the ongoing AI research so far, is that humans create the parameters, machines optimize and apply them, and humans recheck machine progress to see if the parameterization is successful. It's a very workable flow. In logic, humans intuit new system axioms. Machines then apply those axioms to determine truth or falsity of a large class of problems. Okay, and so when we need to expand that class, humans need to intuit a new system axiom, then the computer can then apply that axiom to a larger set of problems. Okay, so a generalized flow. Humans perform a creative task. Humans introspect to determine the underlying parameters of the task. Humans encode these parameters into computers. Computers optimize relative importance of parameters. Computers then apply the parameters to a problem, and humans recheck periodically to verify that no new information is breaking the previous parameterization. And so one thing that I think has happened is that the explosion in specific abilities in AI has caused people to think that strong AI is just around the corner. And that because anything that you can think of that humans can do, we can train a computer to do. Okay? But the reason why it is both unlimited and limited at the same time is simply that humans have to lead. We figure out how to do something, and then we train the computer to figure it out along the same parameters. We train the computer what the parameters of the problem are, and then it can follow along behind us. Okay? Now, the computer can actually apply those parameters to a larger number of problems than we could. So there's actually we'll solve some piece of the problem, we'll intuit a parameter, and once we have that parameter, the computer can then solve 10,000 problems that we've never solved. So it looks like the computer is advancing, but it's actually advancing, the human has to advance ahead of it. So there's no strict limit, but it limits an established limit of priority. So then we come to the field of artificial intelligence. And this is basically including humans in the artificial intelligence loop. Okay, so in typical computer flows, the human asks the computer to perform a task, and the computer does it. But some automation tasks are best suited by having computers ask humans for assistance. Okay? So using humans and computers for tasks that they're each categorically better at is a better process design. And so using humans for what is traditionally considered AI work is known as artificial intelligence. So we throw an actual human in where we would be throwing in an AI, also known as a human-in-the-loop system. So for example, if you wanted a program to categorize images, right? Categorizing images is pretty tough task for even the most advanced AIs. You would just do something like this. You'd say function categorize image, here's a directory of my images, here's a list of categories for each file and directory. Category is ask a human to categorize the file and the list of categories. And so that will send out the job to a human, the human will respond, it will come back and categorize. And so there's actually a number of platforms available that do this. Amazon actually has one called Mechanical Turk. There's a couple others, Microworkers, ClickWorker, Crowdflower. A lot of these are called crowdsourcing platforms because you could also use them to spam people's websites and whatnot. But there's actually some great computation tasks you can get them to do as well. You can use AI in machine learning. There's a system called guided search. For example, in guided search, this is used if you have, let's say you're trying to find, you're trying to train a machine to identify problematic, not safe for work photos in an advertising system, right? I forget the term for it. When stuff you don't want, things, content on, yeah. The problem is that percentage is actually so small, as far as the sample set goes, is that they usually wind up not being classified at all. So in a guided search, the oracle, which is the human, the oracle identifies the specific. They will get together a class of data and say, oh, we especially want this data classified, and so they'll shift the relative frequencies of the data that it hits to make the classification work better. There's guided feature labeling, where the oracle identifies the features that are important for classification, and then the computer figures out the relative weights. Identifying unknown unknowns, where an oracle identifies likely misclassified edge cases. And then there's imagination sampling, where the oracle identifies plausible options in the hypothesis space. So in short, I would say AI works because there is a theological divide between the nature of humans and the nature of machines. And better understanding this divide leads programmers to utilize the best combination of human and computer for any given task. So that's kind of the main thing. I've kind of got a couple slides on others. There's a book called Startup Nation, and they have the story of fraud sciences. And they actually use moral theological reasoning to come up with a model of identifying fraudulent transactions. And basically they said, you have good people and bad people in the world. What do the good people do? Good people aren't really concerned about leaving traces of themselves online. Bad people try to cover their tracks. So what we're going to do is that if of transactions of a certain size, we'll go out and find to see if this person leaves traces of himself on the net. And if they do, then they're probably good. And if they're bad, if they don't, then they're probably shady. And they actually use this to better, I forgot what the actual number was, but it greatly bumped up the percentage of fraud cases that were identified in a much shorter time frame as well. Limiting the eye of AI. A lot of organizations have found they can have better AI responses when they limit the intelligence of AI. So for example, Wolfram Alpha, they figured out, this again comes back to the halting problem. When you try to make the computer do anything, it winds up not working because it really can't process like that. But if you take certain things out, you'll find that what's left is actually still really powerful. It's just not full AI. In fact, there's actually a lot of posts on Medium about Slackbots and about how really trying to be too intelligent is not the way to go. What they do is they mostly use AI for context tracking and natural language processing. And then they basically, the goal is to minimize interface friction. Okay. Another place is that if we view humans as spiritual beings, that we need to take into account their spiritual needs, because we got people more and more on computers every day, right? And they spend more percentage of their time on computers every day. And so when people are only spending a couple hours a day on computers, attending to their spiritual needs was not a big issue. But now that people are all day on their phones and their computers, this is actually a much bigger issue. And so there's a few places that we can take into account. The architecture, John Ruskin in the 1800s was an art critic who talked about architecture and how it can fulfill spiritual needs. And I think I don't know what the answers are here, but I think someone needs to do a similar study today on how software can better adapt and react to people's spiritual needs. Did anyone see the movie Whiskey Tango Foxtrot? Basically, what happens is, one of the things that happens in the movie is that there's this well that keeps on getting blown up, apparently by, Al-Qaeda, ISIS, someone. But actually what happens is, so the U.S. Army dug the well, okay, and they dug the well so this community could have better water and whatnot. Well, the women of the community, the only time they got to talk to each other was when they all walked together to go get water from the river. And now that they have this well, they don't have any place to talk. And so the women were actually at night taking these old Soviet landmines and blowing up the well. The well was just right there, and it was super convenient and easy for everyone, but it killed their social interaction. They needed that interaction with each other, and the well destroyed it. And so anyway, it's so we always concentrate on how do we do things most efficiently, right? That's always what we want to know. How do we do this? Is an inefficient process. How do we do it more efficiently? But that's not all. That's not the only thing that humans need. So Slack does a good job. Kind of first steps. Welcome people to the system. Today is a great day. I don't know all the things Slack says when it starts up, but it always tries to start you off saying, "Aren't you special today?" Another thing is user response emotions. I forgot what company it is, but there's a company that their user feedback, they started asking people how they felt. How do you feel? And just asking that decreased how irate they were when they called. Okay? And the reason is because they had an outlet, right? If you don't ask someone how they feel, the only way that they can communicate that to you is by yelling at you. But if you ask them how they feel and they say, "I'm pissed off," well then that's out of the way, and we can actually talk about what the problem is, right? And their problems in user response went way down because they gave people an outlet for how they were doing. Additionally, software development needs to take into account the spiritual needs of its developers. There's another thing John Ruskin talked about with architecture. John Ruskin went a little bit too far. He wanted to have every piece of architecture handmade. He wanted all the bricks handmade and all this kind of stuff because it put you in contact with your creation, right? And he said that it made it more fulfilled workers, right? It might be true, but that's going a little far. But nonetheless, we have to take into account the needs of developers in, if they're going to spend their lives building things, they need to have spiritual fulfillment in what they're building. Another one, and we're almost at the end, software complexity management. If you know which parts of your code require creativity to create and manage, this allows you to better allocate your resources. You can actually identify certain patterns of code that require more creativity to handle. So once you know those, you can actually mark parts of your code for extended review for each release, that sort of thing, and you can better handle your complexity. And you can also, if we standardize stuff like this, we could better market our to investors and stuff like that. We could say how valuable it is based on how much creativity we have packed into the program. And then here's additional things I've thought about: likely locations to need Oracle performance or spiritual reflection. One of which is recursive behavior. Okay, this is one thing that is actually very awful for both for both science and computers to predict, because you can't actually do it mathematically, because That's where you get chaos theory, is actually from recursion. It makes it unpredictable. Dealing with concepts of infinity and totality, quality versus quantity. So, for example, if your doctor wants to check how sick you are, well, one of the things they'll do is check your white blood cell count. If you have too many white blood cells, you have an infection, right? Well, someone can say, "Oh, I can solve that. I'll just kill all my white blood cells," right? That doesn't work because it's just an indicator, right? And so, separating out, being able to separate out what is the thing versus what's an indicator of the thing. Okay, and this is, in economics, they actually call this Goodhart's law. And that's any number that you use as a quality statistic will very quickly disappear. Once people start targeting that number, once you start thinking about the number rather than the thing that the number is supposed to signify, then the number ceases to be useful. Okay? And so that's something that we can understand as spiritual beings, but computers can't understand that, oh no, because computers are all about quantity, so they wouldn't even notice that the quality is off, because the only thing that they can even see is the quantity. As we've been talking about, is dealing with non-mechanical causal sources like ourselves, dealing with problems that are not amenable to mechanical solutions, and this is kind of restating the previous one, analyzing for non-quantifiable values. All right, so that is solving engineering problems using theology.